Welcome back to the next video, everybody. Today's video will be the final video before we embark on the actual proof of solvable n equals 2 Langland's reciprocity. Today, we're going to say a little bit about the trace formula, A, because it actually popped up in some of the previous results in the last video that were specific instances of Langland's functoriality, and B, because it will pop up in the proof that we're going to do starting next week. So I don't know a whole lot about the trace formula. This is one of my weakest areas of knowledge, but I'll tell you what I do know, and I'll give you some references. So, I mean, what is this chapter about? The right regular representation R0 of G of the Adels of F, or G is some reductive group, in the space of cusp forms L2 0 of the orbit space GF slash GAF, comma omega, decomposes into components pi. These are the cuspidal components pi of the right regular representation. These have been the focus of our study of automorphic representations of G since the get-go initially, or once we generalized sufficiently, let's say. The thing is, given R0, you can't say much about pi, unfortunately. Okay, so that's the motivation for the trace formula. So let's make an operator that's also called R0 in the following way. Take f of G to be some sufficiently nice, compactly supported what we'll call test function on G of the Adels of F. F is our number field. And let's define an operator R0 of F on this L2 space by the following formula. R0 of F will be the integral over the orbit space Z of A sub F slash G of A sub F, where Z of A sub F is the center, of F of G R0 of G dG, okay? Where R0 of G here refers to the original definition of R0 above. And the formula is actually a little bit more complicated than this. This formula assumes that the central character omega here of R0 is trivial, but we'll just kind of see what's going on in that simple case, and we'll just keep it nice and easy. Okay, linearity of the trace essentially gives me that trace of R0 of F is the sum of the m sub pi's from up here in the decomposition of the representation R0 times trace of the pi of F's. Okay, where the pi's are the local components of R0, thought of as the right regular representation. Okay, so again, the problem is I can't say much about the cuspidal components pi of R0. Because of that, I can't actually say much about the trace of this operator R0 of F. And so enter the trace formula. The Arthur-Selberg trace formula seeks to give another formula for this trace. And then you can compare the two formulas and maybe say something about these cuspidal components. Okay. So in Selberg, harmonic analysis and discontinuous groups in weakly symmetric Riemannian spaces with applications to Dirichlet series, that's quite a long title there. The author finds that in the case G is a semi-simple Lie group with discrete subgroup gamma, and you should think like, what are those applied to our specific situation? Those will play the role of G of the Adels of F and G of F respectively. Then if the orbit space gamma slash G is compact, then if we replace gamma slash G with G of F slash G of AF for clarity and specificity, the author finds the following. Trace of R0 of F is also given by the following formula. Sum over brackets gamma, M sub gamma, phi sub F of gamma. The sum runs over conjugacy classes bracket gamma in G of F. And these M sub gammas are just integers. And each phi sub F of gamma is what we call an orbital integral. And I won't say much about these, but they're given by these integral formulas here. Integral over what we call G sub Y of A slash G sub Y of A sub F of G, F of a conjugation of gamma by G, basically. Okay, so what is the Arthur-Selberg trace formula? So later in the 70s, Langlands develops a general theory of Eisenstein series that works for any reductive group G. Okay, and then Arthur, so James Arthur, used the theory that Langlands creates to create a trace formula for not necessarily compact quotients of G of F slash G of the Adels of F. And here's the formula. It can be written very elegantly. The sum over O of J sub O of F equals the sum over chi of J sub chi of F. The left-hand side is called the geometric side, and the right-hand side is called the spectral side. The left-hand side is a sum of special types of equivalence classes in G of F, very simply. And the right-hand side is a sum over certain classes of automorphic cuspidal representations of what we call Levy subgroups of G. And again, for more on special subgroups of reductive groups, I would recommend that you study up pretty seriously on your linear algebraic group theory from Springer or from Milne or someplace like that. Okay, now where did the trace go, right? It's still present actually, because certain terms on the spectral side here actually add up exactly to the trace of R0 of F, which is the thing we're trying to work with, right? So how do we use the formula? Well, Langlands had the idea to compare the trace formulas for two different groups, G and G prime. This allowed him to find functorial relations between their automorphic representations. If you look in Jacques Langlands, this idea is chased essentially to establish a correspondence between automorphic cuspidal representations of G equals D cross and G prime equals GL2, where D is a division quaternion F algebra. Okay. So how did this show up in the last video? Well, you can apply this idea here to the case G is GL2 and G prime is the restriction of scalars functor res E over F of G. And what do you get? Well, we find if we do that, we just find ourselves returning to the idea of base change. Okay. And in the proof of base change, the trace formula is invoked to the surprise of nobody. Okay. If you want to learn more about this, like I'll tell you what I'm going to do when I get to the stage. The trace formula is very deep. It takes a lot of effort to learn all the background, to derive the formula, to understand and to utilize the formula. A great place to start is a very new reference, Getz and Hahn, An Introduction to Automorphic Forms with a View Towards Trace Formulae. And then there are more advanced texts on the subject, but you can read those after, and you can pursue the references found in this book. I think this book is a 2022 book, actually. It's very new. Okay, so finally, so starting next week, we will finally push towards the proof of Theorem 9, which is all that's left if we want to prove automorphic Langlands tunnel. It's a special case of n equals 2 global Langlands reciprocity in the case that we're dealing with a solvable group. Okay. And so I will begin doing that next week. Thanks for watching, and I'll see you then.